Hello and welcome back. So, in embedded systems, one of the challenges is once you've uploaded your firmware onto your hardware, it's sort of difficult to know what's going on, especially if the firmware isn't doing what you expect it to do. And one of the commonest approaches that we use during development is maybe just to see if your firmware is executing a particular function based on a condition. You might want to turn on some LED to say, okay, yes, it is at this point turning on the LED, so then I can believe because of where I wrote the code for this LED to be turned on, it is running this particular code, right? It is not like traditional programming on PCs where because you already have a screen connected to your processor, it's easy to log things out and see them. However, we are able to achieve a similar thing in embedded systems. And in this video and the next video, I'm going to show you two techniques that Zephyr makes available for you to log information or data from your microcontroller and also makes it possible for you to view them on your host computer. Now, before we get started, let's think of it this way. Your microcontroller doesn't have a screen connected to it. So if you log information, like in C, if you use printf, it writes to the console, but your MCU has no console. So how do we get this information out? And this is why in Zephyr and in many other embedded systems frameworks, they leverage one of the serial communication techniques, and it's usually the UART that is chosen for logging information. So basically, there's going to be a UART connection between your microcontroller or your hardware and your host computer, which is a computer on which you are writing your code, compiling and uploading onto the MCU. And because of this serial communication link between the two, you can write something from your microcontroller and it's going to push that data through the link onto your host computer. And so there has to be a software on your host computer side that is able to take this information from the serial communication and also present it to you. And this is what has been leveraged in Zephyr to provide the two different approaches I'm going to teach you about. So, the first thing you need to remember is that for this particular exercise or video, the board you use should have a UART to USB converter built on it. Otherwise, then you will have to use your own UART to USB converter to be able to carry on the exercise that you see in this video. I'm mentioning this because it's easy for you to assume that because you connect one side of your MCU to the USB cable and the other side of the USB connector goes to your computer, it's easier for you to mistakenly assume that there is a UART USB connection. That is not always the case. Sometimes the USB cable is just for uploading firmware onto your board. I am using this board here. Let me try to switch to where you can see me. Yes, so I am using this board here. The board is Nucleo F411RE. And if you read about it online or if you read its user manual, you will see that it actually has a virtual COM port. So they leverage the ST-Link setup here, and it is some way somehow in the hardware connected to the UART2. So this has multiple UART peripherals, and there is a connection between the ST-Link that actually handles the upload of code to the MCU and the UART2 of this board. So this particular Nucleo board has a USB UART converter built in, or a virtual COM port built in, and that is how we are able to send information from here and then we get it shown on the computer, okay? So you just have to make sure your board has that. If it doesn't have that, then you have to find yourself a UART USB converter. I think I showed some in the very first videos, and then you use it to establish the connection. Okay, so now let's go to the code. You can see that I'm using a function here called printk, which has a similar structure to the printf function that ships with C by default, right? Now, what this printk function does is it behaves exactly like the printf function, but instead of writing the output to a console, which of course it cannot because there is no console on your MCU, it writes it through whatever UART peripheral has been designated to be used for that purpose, right? And so it has the same function signature, the same way you can use placeholders. So in this example, you can see that I've declared an integer 37, a float 32.87, a character, and I'm storing a in there. And on line 8, I'm printing hello world, just hello world, right? And then I put the carriage return here so that it will go to the next line. And then on line 9, I'm printing the integer is, and I'm using a format specifier here, which is a default format specifier for integers in the normal printf function that you know. And then I tell it, so it's basically going to substitute this inorm in place of this %d. And then I said the float is %f, and I could let it just print out this float directly, but there is an implicit conversion that okay, so I'm just doing it explicitly by converting the floating point number to a double precision floating point number. No value is lost here. It's actually a promotion, right? And then you use %c for character. So all the format specifiers that you know about in traditional C when you are running on a computer actually works here. And I'm going to compile this code as always. Nothing has changed, and I'm going to flash it onto the microcontroller. Okay, so now it is flashed onto the microcontroller. The question is, how do we see these things that we've printed out on the host computer? Remember I said that it is leveraging the virtual COM port on the board that I showed you to be able to stream this information from the microcontroller onto the host computer. And the traditional way or the normal way that we use to see information that is sent over UART is to use a serial monitor, right? Now, the VS Code plugin comes with a built-in serial monitor program. And just as you might already know, if you don't know, that's okay. The next few videos after the login is going to be about serial communication, so then you will understand what is going on. But there is basically information being exchanged between the microcontroller and the host computer, and they have to agree on what is known as a baud rate. That is the rate at which information is sent, right? So how many bits is pushed per second. They have to agree on that. There are standard baud rates here, a lot of them, and I'm choosing 115/200. Not because I am choosing it arbitrarily, but because my board has been configured to use 115/200 as a default baud rate. I'll show you where I'm seeing this. So you have to come down here and then choose the particular port. And I'm on a Mac, so I'm seeing STM microelectronics. I've tried it and I've seen that this is what is the virtual COM port on my board. If you're on Windows, you might see virtual COM and then some COM number. Try the options there and then you see the one that works. Or you can also read the reference manual for your board to know which particular port you have to choose for serial communication. So now if I click Start Monitoring, the PC is connected to the microcontroller through the virtual COM now, okay? And so whatever the microcontroller writes through that channel will appear on the PC. And in a similar way, I can actually type something here and send it to the microcontroller. But in this code, we don't have any part of the code that is reading what the host computer will send. So I'm not going to bother you with that yet. Now, this program has already run, and it's run before I started monitoring, so I'm not going to see anything. So what's going to happen is I'm just going to press the reset button to rerun the program. And once I did that, you can see that hello world has been printed, and indeed that is what I printed on line 8. And you can also see the integer is 37, but you can see that the rest of the things I printed do not go on to the next line, and I deliberately did that. The reason is that this is serial communication, and for the cursor to move on to the next line, you have to give it a carriage return, right? So slash r slash n, I put that here, and then I put slash r slash n also here, and I put slash r slash n also here. And then let's recompile this program. I'm going to stop the monitoring, so I will upload the code onto the board. All right, code uploaded. So I come here, I start monitoring, I press my reset button, and then now you can see that hello world is on its own line. The integer is 37 is on its own line. Everything that I have printed is on its own line. Now let's go into the details. Like I told you, I'm choosing 115/200 for the baud rate, and the question then is, okay, how do you know this is what you have to choose? Remember, we spoke about device tree source, right? And I mentioned to you that the device tree source is how we describe hardware to the Zephyr framework. Now, if I open the device tree source for my board, and my board is a Nucleo F411RE, so how you get into that is you have to go to your Zephyr workspace, the Zephyr workspace you are using. So I'm in my STM32. You go to devs, Zephyr, boards, and then you go to the manufacturer ST. You look for the folder that looks like the name of your particular board, and then you will see the device tree source and its includes and stuff in here, right? So this is the file that I have opened. Now in here, I told you that printk is using UZAT2. Sometimes I say UAT, sometimes I say UZAT. In the next section, you'll understand why they are the same things, okay? So how do I know it's using UZAT2, and how did I choose 115/200? And as you can see, I'm choosing 115/200 because that is the current baud rate or the speed that has been set in the device tree source. So the hardware has been described to Zephyr to work on UZAT using 115/200. And you know, it's even showing the pin controls here. So this is on port A pin 2, that is for the transfer, and the receive is on port A pin 3. Again, if you don't know anything about UART, don't worry, there's an entire section coming up that is dedicated to serial communication. But if your board doesn't have a built-in virtual COM and you are using a UART to USB converter, these are the pins you want to connect. I will also again explain that in the UART communication section. I just want this to be a video about logging. So this is how I know it's 115/200. And how did I know it's using UZAT2? I know that because I've read the reference manual of my board, and it tells me there is a virtual COM port on UART2. Now, one more important thing here is there is also a default config here. And this file is also found in the same folder where the device tree source is, right? Now, in Zephyr, it uses something called kconfigs, which is borrowed from the Linux way of doing things. And kconfig is how you enable certain functionalities of the SDK and also the build toolchain, right? So by default, I mean, having the defconfig file open here and seeing config console equals y, the y is yes. So this is what enables printk to send its output through the console. So it's using the USAT or UAT2 as a console, and this is what is enabling the printk function to push its data so that we are able to see it on the serial monitor down here. So anytime that I press the reset button, because it's not the code is not in a loop, so it runs once, but anytime I press the reset button, it's going to rerun the program and it's going to print out the same over the UART communication peripheral. Now the question is, what if we didn't find config console equals y here? Anyway, you can override whatever default configurations you have in your application. So let me come to our playground here. You can see that there is a prg.conf, like project config. In here, we've enabled GPIO. So you have to actually enable this for you to be able to control GPIOs. And even if we didn't do it, it was going to work because in the default config, GPIO is also enabled already. The same thing applies here. So I can just paste this here. Whatever you put in the project config overrides what is in the default config. So if I say config console equals y here, is the same. I'm basically enabling the build tool to work with the printk function and also to use the UART as the console. One more thing you need to remember is this include here. The printk is not part of C by default. So you have to import it by including Zephyr /sys/printk. Having said this, I'm going to say one more thing. The printk function is an in-place logging technique. What it means is that it can have negative timing effects on your firmware. Like whenever your MCU encounters a printk, it is not going to execute what comes after it until the printk function has finished. And remember, this is a write operation. It is writing over a communication channel. And these are some of the bottlenecks in programs, right? And so until all the bytes have been written to the UART peripheral, your program is not going to continue. And this is what makes it bad. It's called an in place. It's not buffered. There is no thread, the separate thread that is handling this logging from the core logic of your firmware. So this is one thing you need to be careful about. If timing is of the essence in your firmware, then you want to be careful how you use printk or to stay away from it entirely. Having shown you the disadvantage of this, in the next video I'm going to show you a more robust logger module that gives you more control, such as being able to log at different levels, the log message itself having some more details, and also being able to filter them out. Sometimes you want to see some logs when you are developing, but in production you don't want to waste the microcontroller's time by logging because nobody's going to look at them. And the module we are going to talk about next actually allows you to be able to do that. So thank you very much for watching this, and I will see you in the next video.